for integrated energy systems. Yeah, okay. The podium is yours.
Hi, I'm Dayo, and glad to be here. I know everyone is very tired right now. I am. So many different ideas floating around. Hopefully I remember what I'm here to talk about. So I'm from ENN, and we're a MITI member, MIT Energy Initiative member. Thanks a lot to Wendy from MITI and Hongmei from ENN for that. And most of us are from ENN, except for 3. So Bo Long is the head of AI Foundation at LinkedIn. Bin Pan was an engineering manager and tech lead at Uber, and he recently left for DD Labs. And Jingfan Wang is a grad student at Stanford. So today I want to talk to you about our work on an optimal dispatch model with dynamic power curve for integrated energy systems. So by dispatch, I mean scheduling, hour-to-hour scheduling of the devices. By power curve, I mean the efficiency versus load of the devices. And by integrated energy systems, I mean those energy systems where we explicitly take into account the combination of different energy types. So it could be at the source, where you could have PV input, you could have electricity from the grid, you could have natural gas. At the device, you could have energy coupling between at the devices themselves, like CHPs, combined heating and power, or CCHPs, combined cooling, heating and power. And also at the sink, energy users are also using different types of energy. They're not just using electricity. Sometimes they use heat, they use hot steam, depending on their industry. So that's what we're going to talk about now. So we're going to start with a little bit of motivation, look at one particular challenge, analyze our approach, and focus on the application, analyze the effectiveness of the approach on one particular application, and conclude. So being a company, and not from, from a university, our motivation is actually money. But we can't really put a dollar sign here. We won't be invited if we put a dollar sign here. So I have to put a fancy diagram here. And also one of the questions we had was, how would renewables affect our dispatch? So that's one lingering problem we have. And typically, in such cases, we can model this as an optimization problem. Such an optimization problem is typically a mixed integer nonlinear program. And the nonlinearity in this case primarily stems from the nonlinearity of the devices. And that would be our focus. So today, we only have one focus, one idea. So in particular, the power curve, efficiency versus load, how do we model that? So what is a device? Well, a device, in abstract terms, is a dynamic system. And then it has many different influencing factors that are changing over time with various different types of uncertainty. And if you look at devices, so energy stations are a collection of devices. So then you're dealing with potentially different sets of influencing factors with changing differently over time and with different uncertainties. So what are some ideal properties we would like from modeling devices? Well, maybe we want it to be uniform. Well, uniform so that we can be lazy and do one type of mathematics. We don't want some sort of complicated mathematics for one device, another sort of complicated mathematics for another. It's very difficult to compose those models. And data-driven so that we can be lazy and say, oh, hey, whatever influencing factors there are, this is the data. That's the truth. That combines the externalities as well that direct approach models might not consider. We might want it to be robust so that the result of the model and the decisions based on those models will not be fluctuating wildly, flip-flopping as we perturb the parameters just by a little bit. And maybe even stochastic. We know that there's uncertainty in this world. What if the model gives us uncertainty, stochasticity built in? Then that would be great, right? And the approach is Gaussian process regression. So Gaussian process, you can think of it as a stochastic process where every finite collection of the random variables in the process is actually jointly Gaussian. So the bottom line is this. If you're willing to use Gaussian to model your phenomenon, including the noise, then it follows from the multivariate Gaussian theorem that everything else is Gaussian too. So the marginal probabilities are Gaussian, the conditional probabilities are Gaussian too. In particular, the posterior probability is also Gaussian. The posterior probability of what? The posterior probability of, given the data set, given a X star, a load value that you haven't seen what its efficiency is. You want to predict Y star. That is also Gaussian. And looks like Meng, who gave the talk on SVMs earlier today, is not here because, and that's good because there's a tutorial on Gaussian processes or why I don't use SVMs by Zobin, and I encourage you to read that. It's a very good tutorial. So this is a comparison between a direct approach versus a Gaussian process approach to modeling devices. Well, a direct approach, you might start by each specific type of device, and you come up with one model for each specific type of device. That's one way. The other way is Gaussian process regression, and we just talked about it. Everything is Gaussian, so the mathematics is dramatically simplifies. And also, the direct approach requires you to base on first principles, which I don't know. I'm not a physicist. So the Gaussian process regression, you could base it on data and lazy or even online learning. In particular, as the device ages, the parameters definitely change, right? So the data-driven approach naturally takes that into account. Also, in the direct approach, usually robustness is very hard to calculate and bound. And here, Gaussian process regression makes that much easier as well. Stochasticity is also built in naturally as part of the model. You can come up with a confidence interval of the prediction. So here's an example. So applied to a gas steam boiler. This is actual data of one of our integrated energy stations. And you can see that the Gaussian process regression achieves the lowest root mean square error. And here's the 95% confidence interval I was talking about. So stochasticity, uncertainty is naturally built into the model. So going back to our original problem, the dispatch problem. Now, how do we fit this back into the dispatch problem and solve that? So we have the modeling of the devices, and the rest of the constraints are actually easier to deal with. So then we formed a nonlinear program, and then we actually linearize it by using special ordered sets of type 2. And the reason we do that is because it's much easier to solve. And in our experiments, we find that this gives us acceptable performance. And then we solve it by, say, Cplex. And here's the application. So we want to solve the dispatch problem on real energy stations. Unfortunately, our real energy stations are not as diverse as we like, the so-called integrated energy stations. So what we did here was to combine real stations, real data from one of our stations, anonymized as station A, and then another PV station anonymized as station B. And we also might have a set of storage, simulated storage batteries in between. So, and that's your A plus B, although it's not action plus baby, but it's also A plus B. I think that's why we were accepted here. So, and we have some underlying assumptions in this application. For instance, the price tariff structure. John talked earlier about the Guangdong electricity market opening up. And so part of the reason, part of the motivation I didn't talk about earlier for us doing this is to make sure that we're ready when the electric power market opens up. We're ready, that we have some sort of a dispatch model that can guide our decisions on what types of equipment to use and when. So we analyzed 3 cases. In case 1, stations A and B that I just talked about. So station A has 2 CHPs and 3 gas steam boilers. So it outputs both steam and electricity. For simplicity, here we will focus only on the electricity load. And you'll see plenty of diagrams later on. But the optimization problem is also satisfying the constraint that we need to satisfy the steam load. So case 1 is the case where stations A and B operate independently and there's no storage. So what's the combined profit per day? So that's about 43K yuan per day. Case 2 is we virtually integrate stations A and B together without storage. What happens then? Well, we find that we have a 3.4% increase of gross profit per day. And case 3 is if we integrate virtually, again, virtually integrate stations A and B together with storage, then we get a 5% increase with respect to case 1. And here's case 1. So again, this is only the electricity dispatch, not the steam. And you can see that, so the positive part is a supply. You have various different types of supply. You can buy it from the grid, which is the yellow parts. You could generate it yourself using CHPs 1 and 2, different colors. And then the lower part is the demand. So here we only have the power demand of users and possibly some power sold to the grid. There's a little bit here. So you can see that because of the price tariff structure, at the earlier times of day, because price is cheaper, we just buy it from the grid, and there's no steam load. So we just buy it from the grid, we sell it to the users, done. Later in the day, as the prices of electricity increases, we can no longer buy it from the grid and sell it to the users directly, making a profit. We have to generate it ourselves. So we use CHPs 1 and 2 to generate it. And also, again, satisfying the steam load. That's not shown here. So that's the dispatch. So this is the hour-to-hour dispatch. At what times should you use which types of equipment and purchase from grid or selling to the grid? So case 2 is virtually integrating stations A and B, and again, the electric dispatch in this case. So here we have, in addition to that, what we have earlier, we have the PV power generation here. You can see that as PV power comes up, right? So we start selling it to the grid more, and that's this part, right? So that's not surprising at all. And then case 3 is we virtually integrate stations A and B together with a set of simulated storage batteries. What happens now? Well, unsurprisingly, but happily, you see that there's energy arbitrage going on. When the energy prices are cheap, we buy it from the grid and we store it, right? So we store it into the batteries, and later on, when the prices are high, we discharge, we sell it back to the users. Oh, oops, what happened? Okay, yeah. So we only have one idea, and that is Gaussian process regression is good for modeling devices, and that storage and renewables go hand in hand, just like Jerry mentioned today in the plenary keynote. And they do go hand in hand. In particular, there's an increase in profit per day. There's lots of work missing here. And we could see if mixtures of Gaussians help. We could apply GPR to other aspects of the model, even though I told you that, Gaussian process regression gives you stochasticity in the model itself. We haven't really looked at stochastic programming here at all. So there's lots of work to be done. And we really want to look at more real-world energy stations. And whenever you're looking at virtually combining data, you have to think about what if the scale mismatches, right? So what if the station A has a very large load and station B has a tiny load? So how do you scale it up proportionally so that it actually makes sense? So there's lots of work to be done. And we'd like to thank a couple of our co-workers for valuable discussions. Thank you. Yeah. Oh.
Okay, we have time for questions. One question, okay. Yeah, go ahead.
I want to know your Gaussian outside the pre-hour information about your.
Oh yes. So for Gaussian process regression, you do need the prior information, and the prior information, it's also up to you to choose the mean function and the covariance function. So that's one way you can change your prior, yeah, if I understand correctly, yeah.
I think you have an understanding for model, because I think your model just can deal with the continuous function. But so in reality, and for CCTT,
Yes.
yeah, for CCTT, its performance function is not. Can you
Right, so Sure. I think if I remember correctly, we have considered that, but I don't remember what we did and why we actually ignored that part in this analysis. Yeah. But we can talk offline.